have also isoelectric focusing. Okay, we will go one by one for the sake of to know the protein can also be separated by using according to the charge. Okay, so charge of the protein. Different protein have different negative charge and overall charge will depend on the sequence and the pH. Okay, if you still remember, we have 20 common amino acids. Okay, this is the common amino acid sequence. Amino acid come with this C, C, O, O, H, H, and then R represent the functional group, and then NH2 represent the amino group. And then we have each protein, each amino acid comes with its own PI. For example, the PI of this is supposed to be in small, yeah. And then, yeah, this is the PI of the protein. So imagine you have your peptide last time, it will come with different PI. Okay? So the PI is depending on the R group. Okay? I will repeat this section in case you need some clarification. We have here, this is the basic structure of amino acid. Okay, amino acid is a building block for a protein. For our case, we have T1 lipase. So T1 lipase consists of 388 amino acids, the mature part. Okay, the mature sequence of 300 of T1 lipase consists of 388 amino acids. So we have this 388 of this in T1 lipase. Okay, so we start with N terminal to C terminal, and then this functional group will determine what is the PI of T1 lipase of particular protein you are working on. So when we say that our protein can be separated based on the charge, meaning that because this one, this is the, for example, if this is your N terminal, the first amino acid, and then the extension of amino acid, of the protein is based on this side, right? From N to C terminal, okay? And then this one will be combined with the another amino acid. Okay. So only this side basically will give you the charge or uncharged, depending on this side. Okay. So if the PI of T1 lipase is around 6.31, okay. If you want to separate protein based on the charge, we can separate the protein based on the current charge of the protein. Okay. How do we determine? Either we want it to be positive or negatively charged. If you still remember, we can set the protein. We can set the protein to be positively charged or negatively charged. Okay, how do we set? Based on the pH, right? If the pH higher than PI, protein will be negatively charged. If the pH lesser than PI, pH lesser than PI, protein will be positively charged. Okay. So we have the PI of T1 lipase 6.3. If the buffer we use, for example, glycine sodium hydroxide, pH 3.1, which is similar to the PI. The T1 lipase will not be solubilized in that buffer. Okay, so we don't want the buffer similar to the PI. Okay, so if we want the T1 lipase to be positively charged, if you want the T1 lipase to be positively charged, meaning that the pH need to be lower than 6.31. Okay, pH. If you want T1 lipase, we want T1 lipase to be positively charged. We use the buffer lower than the PI. The buffer should be maybe 6 or 5.7. Yeah, depends on the how many charge we want. If more, if we have the pH is too low, that means the strength of the positively charged will be higher. Okay, if the pH is too low, for example, the PI is 6.31, but if we choose the pH 4.4, can you imagine how positive our protein will be, right? As compared to if you use the pH 5.8. 5.8 still lesser than PI. pH lower than PI. 5.8 pH lower than PI. It will give you positively charged protein, but not as strong as if we have here. If you want the protein to be negatively charged, that means the PI, the pH should be maybe 7. If we have pH 7, you see, higher than PI. pH higher than PI will give you negative charge. So if T1 lipase in a buffer pH 5, the T1 lipase will become negatively charged. But if you use 8, definitely 8 will make T1 lipase become more negative than pH 7. At pH 8, T1 lipase will be more negative than pH 7. Okay, you got it right. You get to know that principle. Then we move forward. Okay. So it depends on the sequence, right, and the pH that we have put our sample. Okay. Do you have problem with this position, or you want it to be like this? Is it okay like this? Okay, I will hold it like this because I cannot make my phone screen bigger than this. Okay. So, okay, yeah, we have discussed about this, about determining the PI of the protein. Okay, if you don't know for the first time, if you don't know about the PI of your protein, just go to the ProtParam. The website. You have to use it that time. Okay. Okay, more protein, more acidic behavior. We have discussed just now. More protein with more acidic residue will have lower PI. More with basic residue will have higher PI. Estimating the charge of protein. What we want to know, okay, yeah, we know once we can set the PI or the charge of the protein, how much positive or negative based on the buffer that we have used just now. Okay. Yeah, for example here, if we have the PI 5, we have more pH, more OH, meaning that higher pH, the protein will become more negative. Okay, if we have more acid, I mean low pH, protein will become positively charged. Okay, yeah, at pH 3 protein will be positive, at pH 7 protein will be negative. Okay, yeah, we have discussed about this. Okay, so we go to this side for the ion exchange chromatography. So we can check on this video for a while. That's the video for the separation based on the this one. Okay, so we have this. Okay, this is where when we say we separate protein based on ion exchange chromatography, meaning that the protein is separated based on the charge. Okay, so in the matrix, okay, in this column, in this matrix, we have uh, the matrix either positively charged or negatively charged. Okay, so for this example, they have the matrix with positively charged matrix. So positively charged matrix will attract the negatively charged protein. Okay, the positively charged matrix will attract the negatively charged protein. Okay, we have prepared our protein just now to be, if you want it to be negatively charged, we need to increase the pH so that the T1 lipase will become negatively charged. Okay, because we want to use positively charged matrix. That means the protein, the T1 lipase, should be in negatively charged. Okay, so if you look at here, all the negatively charged stuff will bind to this. Okay. Okay, for this, okay, so now this is the negatively charged just now is in the phase of equilibration. So now your protein, okay, just imagine the crude protein. When you put your T1 lipase crude in the pH 8, for example, no, I don't want pH 8, it's too high. Let's try pH 7.4. Okay. So now the T1 lipase in a buffer 7.4. That means this will make the protein become negatively charged. Not only T1 lipase, all the protein with lower pI, which just like lower than pH, will turn out to be negatively charged. Okay, in the crude protein, there are 4,000 of protein, right? 4,000 plus 1 protein. Okay, in the pH 4, some of them will become negatively charged because they may have the pI similar to this or lesser than this, but it will turn out to be negatively charged if the protein of the crude is higher than, if the pH is higher than its own pI. Okay, hopefully you can get it. Not only T1 lipase will become negatively charged. Any protein where the pI of the protein is lesser than this pH, okay, will turn out the protein to be negatively charged. Okay, so We go back to this. For example, protein number 1, which is negatively charged, protein number 2 also negatively charged, it will bind to this matrix. Okay, because the matrix is positively charged. Okay, then you can see here the protein trapped on this. Okay, why? Why there's a peak here if the protein attract to the matrix? The protein here represent the unbound protein. What are unbound protein? What is the unbound protein? It is a protein where the protein having similar charge of the matrix. The matrix will attract only the opposite charge. If it is positively charged, only the negatively charged protein will bind to this. The positively charged protein will be eluted out, will come out. Okay. So now the peak here represent the positively charged protein, the positively charged impurities, right? Because they cannot bind to the resin. Okay. The blue color here represent the salt. Okay, the different buffer with different pH. Okay, the gradient. We have explained about the gradient here. Okay, as we increase the gradient, I mean the salt concentration, okay, of course it will come with different pH strength. Okay, so what happened? The protein with first the weakest negatively charged protein will be eluted out. Charged protein will be eluted out, will come out first, followed by the second, I mean, before the strongest one coming out. Okay, so the stronger will come as the second elution. Okay, because we have increased the salt, I mean the buffer here. As we increase, the strength of the negative ion coming from the buffer will flush the negatively charged protein out. Okay, last but not least, you see, this is the strongest one. That's why it will come out later. You see, once we have put the higher concentration, then it is out. Right? So this is where the regeneration section, where we have applied the highest concentration of the salt, or for this principle, we can just say the strongest, I mean the most negatively charged salt, because this salt will take place on this matrix, so that this matrix can be reused. Okay. So any okay. What peak is that again? Okay. The question asks, this peak represent the protein that been trapped here. Okay. The protein that initially trapped in here will be eluted. You see, initially, this is the protein that bind to the matrix. Okay, it bind to the matrix. This flow through matrix, still having the flow through. This flow through matrix, I mean, peak represent the positively charged protein. Why positively charged? Because the positively charged will not be captured by this positively charged matrix. It will go out immediately. Okay. Yeah, what Emma said, the positively charged product is diluted. Yes, the positively charged will come out first. That's why you don't want to essay this section because you know you don't want to. Maybe you don't want to. You don't want to find your trap protein in here, your T1 lipase here. Why? Because you have prepared the T1 lipase to be negatively charged. The negatively charged T1 lipase will just be trapped in here, not in the flow through. Okay. So, yeah, when you come to this section, the illusion part, you need to find which fraction represent T1 lipase. Maybe fraction number 25, or maybe fraction number 28, or maybe fraction number 30, you don't know, or maybe in here at the highest concentration of the salt. Yeah. So we need to know which fraction represent the T1 lipase because we don't know about the nature of the other 4,000 protein. Okay, but at least we have separated the positively charged protein. If we have, for example, if we have 4,001, because this is our T1 lipase, right? But if we have changed the T1 lipase become negatively charged, and then some of the impurities also turn out to be negatively charged, maybe out of 4,001, only 2,001 they are negatively charged. The other 2,000, they are all in the flow through. Why? Because the other 4,000, maybe they are positively charged. Yeah. So at least the T1 lipase has been separated either positively charged or positively charged or negatively charged. At least. So later you will know how powerful is the shift feeding tag that we have used before. Because if we use ion exchange, we can only separate just like this. Okay. So the second part, okay. So this is where if the column is positively charged, for example, DEAE, okay, then the negatively charged protein will bind to this. The protein with PIs, okay, lesser than pH, the buffer will be negatively charged, will be negatively charged and bind to the column. Okay, if the PI higher than pH, the buffer will positively charged and not bind to the column. This is similar principle just like that. Okay, if we use the column negatively charged, okay, for example, carboxymethyl, then the positively charged T1 lipase will bind. Okay, so if you want to use the negatively charged matrix, we change here. Just now we use positively charged matrix. Positively charged matrix, we make the protein become negatively charged. But if you use positive, if you use negative matrix, we want the protein to be positive. Okay. For this condition with positively charged matrix, pH of buffer used will decrease Gradually on exist. Yeah, yes. That's why in the purification we have used the gradient. I mean, this you can do it. But normally if we use manual or semi-automatic, we can only use the stepwise technique, not the gradient. Okay. So if you have this, just now we know that okay, the first eluted protein they are all positive. Okay, and then towards the end we can have okay another peak, another peak, another peak, because we have this line. Okay, this salt line. This line represent the strength of the pH. Okay, pH strength. Okay, if we have higher, that means okay, it will have more affinity towards the negatively charged matrix. Okay, the buffer that the salt that we apply will have more negative than the protein. So, for example, if all the positively charged protein being eluted at the flow through, so we can name it. We can put it simple. Like this one, the first illusion, maybe it is only one positive. Maybe this one is positive three. Positive one, positive two, positive three. Okay, that's the way this salt represent. I mean this line. Um, First green peak is positively charged. Second green peak is return negatively charged. First green peak. Where is the first green peak? Let me check. Yes, first green peak. I mean in here. This is first green peak. It's also uh, negatively charged. Okay, but the strength of that negativity is lesser than this two. Okay, yeah. So like here, positive one, positive two, positive three. Okay. So it's the similar principle. If you use the negatively charged metric, if negatively charged metric, that means the thread protein will be positive. The first illusion will be negatively charged protein. Okay, this principle is for negatively charged, no, positively charged metric, right? Positively charged metric will bind to the okay negatively charged metric will attract negatively charged protein. So the flow through supposed to be with a similar charge. Similar charge with the metric, okay, you go out first. Okay, okay, no, this is not positive. We elute because we are attracting. Yeah, this one will be negative. Sorry, this one will be negative. Okay, because we have used positively charged metric. The positively charged protein will go out first. The negative one protein will go out first. With the negative two will come out second. Negative three will come out later. Okay. You cannot. Okay. Can we consider one type of protein? No. This one peak maybe is a mixture of 50. It's a mixture of the 25 protein. Negative three is a mixture of uh, another 100 protein. It's possible. Okay, because if we illustrate the 2000 protein, which is positively charged, being eluted here, so the other negatively charged protein will be eluted somewhere in here, in here, in here. Okay, so we move. Okay. You can just ask a question in the chat room because I'm looking at the chatting section here while holding my phone. Okay, so where is it? Okay, so yeah, I don't want to read this wordy, but you can understand from the explanation just now. Um, okay, so you decide. Basically, you need to decide, right? The conclusion here, you need to decide either you want to make your T1 lipase become positively charged or negatively charged by adjusting the pH. Okay, and then you decide. If you have decided what kind of charge you want your T1 lipase should be, then you choose the metric. Okay, either you want the metric to be positively charged or negatively charged. Okay, so you do not prepare your T1 lipase to be positively charged and then suddenly you use the metric positively charged, then that means it is so wrong, really wrong principle. Because T1 lipase will just come out here. Can you imagine this 2000 is, yeah. So you need to have proper metric. What kind of metric you want to use? Then you can prepare the pH. I mean, you can prepare the charge of your T1 lipase. Please remember, initially we have prepared the T1 lipase with 7.4 buffer with the PI of this. Why can't we just prepare T1 lipase in the buffer pH 9? Or the T1 lipase will become negatively charged, right? Logically. Okay. The answer is if it is too much. Can you imagine when the T1 lipase will come out after this? Maybe after we have done all of this, still we have many peaks here, and then yet in all of the peak there's no T1 lipase activity, meaning that the T1 still trapped in this charge. We don't want the T1 to be too negative, I mean too strong. Then it cannot be eluted into fraction. So we don't want it to be too negative. So how much negative we need to make it if we have this PI? Yeah, it depends. You need to optimize. Maybe 6.8 is already negative. Yeah, definitely it is already negative. But how good is the negativity for that? So we need to keep optimizing. There's like an endless effort. But you will decide either it is acceptable or not based on your purification later on. So if you have tried with 7.4, it's not good. Then if it is nothing in the peak, okay, maybe 7.4 is really negative. I'm going to reduce this. I'm going to reduce this to 7, yeah, pH 7. pH 7 will make this T1 lipase become negatively charged, but not as strong as 7.4. Okay? So remember, we want the protein to bind to the matrix, but not too strong, so that it can also be eluted later on. Okay. So second part, we can separate the protein based on native gel electrophoresis. Okay, when we say native gel, as compared to SDS, okay, both of them having similar gel. Native and SDS They are similar technique, but different in composition and principle. For native gel, the protein is still in the native shape, meaning that I will clear this. Okay, this is the native state of the protein. For example, the T1 lipase. It comes with this. With another multiple. Okay. Okay, there's a one domain, maybe second helix, and then yeah, um, and then we have two of this helix, big loop or something. Okay, so like looks like we have three domains, one, two, three domains, but these two they are homodimer. Okay, this is only one is unique, and then there's some maybe the disulfide bridge in here. Okay, and then also within this or something. Okay, so when we have native state, meaning that when we load the protein, into native gel, the protein will still in this shape, the 3D structure. But when we prepare the SDS gel, SDS paste gel, meaning that this disulfide bridge is already denatured. I mean, it's been cut. And then plus, not only that, all the protein, I mean all the R group. You see, we have this one, right? CCOOH, CR, and NH two. So all this amino acid, all the side chain. We're talking about the side chain here. All the side chain will become negatively charged. Okay. So if it is what we call it lysine, the last of lysine NH3 plus, right? It will turn out to be NH2. Or the COOH will become COO minus. Yeah, our group for COOH is for aspartic acid and glutamic acid. The R group will have the end of the functional group, we have COOH, right? So if we use SDS, all this will become negatively charged. So the overall protein will become negatively charged. Okay, if we apply the SDS page. If you have the native page, they are all in the native state. They are not necessarily become negative or positive. Some of them may have positive, some of the side chain will be negative or something. Okay. So when we have the native page, meaning that if it is T1 lipase, if the T1 lipase still having the disulfide bridge and all the interaction, all the conformational, it will have in a native form. Okay. So last part for the protein separation based on based on charge is using isoelectric focusing. So any question for the gel? for the page. This is okay, right? Okay. So let me go for the isoelectric focusing. This is where we separate protein based on, okay, we know that protein can be separated by using SDS, just now the gel type, right? SDS page, SDS page, native page, and then we have also 2D, 2D electrophoresis, 2D electrophoresis. So this 2D reprint, okay, meaning that the protein can be separated based on, this is about the protein separation, right? Protein separation. First, the first D is by using isoelectric. The second D will be based on the SDS picture, based on the molecular weight. Okay, protein, okay, separation. If you have used 1D, which is isoelectric point, the second D involves SDS page, which is separation based on the molecular weight. And then basically 2D is not going to end there. We have third D. Okay, it's just the, which is the analysis of the spot. Okay. So if you are talking about 2D electrophoresis, it involves isoelectric point, where the protein is separated based on the PI. Protein is separated based on the PI. For example, if T1 lipase having the PI at 6.3, so the first part, the first D, the T1 lipase will be separated based on the PI, which is 6.31. After completing the isoelectric point determination, okay, running, we will continue with the second D, which is SDS page. The protein will be separated based on the molecular weight, the one that we have done in the lab. Once it is separated based on the molecular weight, okay, the T1 lipase having the molecular weight about 42 kDa, right? So it will be separated at the 42 kilodalton. Band. And then the third D, we want to analyze either that this position is represent the T1 lipase or not. Okay. So yeah, the separation based on the isoelectric, molecular weight, and the spot. Okay. So this is the example. The first part we separate based on isoelectric point, right? In isoelectric, to separate based on the PI, we need to use IPG3. IPG3 means immobilized pH gradient. Okay, IPG3 is immobilized. Okay, for the PR separation, we use IPG3. It is just like this. Okay, it is IPG stand for immobilized pH gradient. Immobilized pH gradient. So this IPG3 will come in the pH range. For example, pH 3 and then pH to pH 10. Okay. So what is the PI? PI is where the protein become at pH where the protein become zero net charge. PI is a PI of the protein is basically at which pH where the protein become zero net charge. Okay. So if the T1 lipase having the PI at 6.31, okay, here, meaning that the protein will travel along this street, will be focused almost overnight. The process taking like overnight process. pH 3 until 10. 3 until 10. If it is 6, maybe it will just stop around here. This is the position of the T1 lipase. Because the PI is 6.3, it will stop around here. If you make it, this is 5. Right? Yeah, somewhere around here. 3, 3, 4, 5. Yeah, maybe not suitable there. 4 here, 5, 6, 7, 8, 9, something like that. So if it is T1 6.3, it will stop somewhere around here. Okay. Please remember that we have the 4001 protein, right? They are all being focused at their respective isoelectric point if we have a complex protein. But if we have just T1 lipase, T1 lipase will just focus and then stop at its PI, which is 6.31. It will just stop at this position because this is roughly at 6. Okay, after this is, we call it the process of isoelectric focusing. Okay, we have the isoelectric focusing machine. We're going to put the IPG3 in this isoelectric focusing machine so that the T1 lipase can travel in this IPG3 until it reach net charge equal to 0. Okay, so what's next? Okay, after that, after you have done this, what happened? The IPG3, it will be placed on this SDS fish gel, SDS gel. Okay, this SDS gel only having the resolving gel, not having the stacking. If you still remember, you have stacking gel up here, right? Represent a comb. We don't want this. Okay. Tissue. Okay. So for 2D, the this part will not be used. Okay. So just the SDS gel using resolving buffer, not without the stacking. So what happened? We are going to place this IPG3 on the gel, on top of the gel. Okay, we're going to place here. So this is starting pH 3 and pH 10. Okay, after that, we're going to run this. Now, so this is high molecular weight. This is where we're going to separate the protein based on molecular weight, high molecular weight, and then low molecular weight. Yeah, this is the T1 lipase. So you see, the T1 lipase now is separated initially based on the pi. Second dimension is T1 lipase will be separated based on the molecular weight. If this is where the 43 kilodalton or 40 kilodalton, this is where T1 lipase will stop. The spot for T1 lipase will stop. Because this is, if we evaluate this spot, that means this spot represent around 6 pi with the 43 kilodalton. Okay. If we compare the 2D with the normal SDS that you have done, this is normal SDS that you have done before, where we have this stacking. Okay. If you have the 45 or 43 kilodalton, they are all been separated here, right? 43 kilodalton in a band shape. But in this band shape, means this band, all the protein, what regardless the pi, they are all will be here. But you have this, okay, only the protein with 6 pi and 43 kilodalton will stop here. But if we have this, imagine, for example, if we have this, if we illustrate this, we may have protein here, protein here, protein here, here, and here, and here. So can you imagine they are all having similar molecular weight, which is 43 kilodalton. But 1, 2, 3, 4, 5, 6, 7. 7 protein with different pi from 3 to 10. They are all being pulled or accumulated at this position, which is 43 kilodalton. Right? Because all of them here will be pulled as one band. And then we just feel happy. Wow, we got single band. Basically, we don't know. There may be a mixture of 1, 2, 3, 4, 5, 6, 7 protein inside here. Okay, so if you look at this image, we have from 3 to 10, 3 to 10, and then they are all from different spot and different molecular weight. But if we analyze these two spots, yeah, we may have, if we have only one D, these two will be together, will be represented as one band, right? Hmm? What happened? Okay, so I think, repeat which part? Okay, so, okay, this is called 2D electrophoresis. The dot, okay, the two dots, okay. This two dot, when we have the RPGs 3, starting from pH 3 to 10, then they are well separated, right? Maybe this is PI 7 and PI 8. But in SDS, if we do not perform the molecular weight, PI separation, RPG, using the RPG strip, these two dots, okay, these two dot number 1 and number 2, they are all in the same molecular weight, right? This is the molecular weight. If this is 100 kilodalton, these two dots will be represented as one band. If we have used only SDS piece and we do not separate them based on the PI. But when we do this 2D electrophoresis, First, they will be separated based on the PI. Second one, they will be separated based on the SDS base. So that we can see here, okay, they are two different protein basically. Want to do the SDS page. I want to do only the PI. What happened? These two dots, the first dot, the top dot, and the second dot, these two dots will be represented as one band in your RPG strip because they are having similar, same PI. Okay? But when we separate them, okay, first based on the PI, second based on the molecular weight, then you know, okay, that one band basically here, actually, they are contributed from the two protein, two type of protein. Protein with uh, 80 kilodalton, another protein with 40 kilodalton. Okay? Okay, Toba? Okay. So, we're going to, yeah. So, for affinity, you have done last time. His tag purified nickel column, and then we have also GST fusion protein, glutathione columns, it depends. So, I don't want to repeat the affinity chromatography part. But we have the HIC, and then amino sulfate precipitation, and then the acidification that I want to show you the principle. Oh, this is all under native jet. No, for the 2D, it is compulsory to use SDS because SDS we want to make sure the movement of the gel 100% based on the size of the protein, not because of the native nature of the protein. If you make the protein become, if you run the gel, if you prepare the lower part of the gel using native pH, this protein will not be in the standard movement because the movement of the protein in native pH is based on the nature of the protein. If it is too bulky or there are lots of negatively charged protein, okay, we run the gel from negative to positive, right? Correct me if I'm wrong, it's from negative to positive. If your native gel, negative, they are positively charged, right? If your native gel is positively charged, meaning that, for example, if this dot in native form, it is positive. It will not move to the end because this end is positive charge. It will just be there, not moving. If we have the SDS page, meaning that the protein is prepared to be denatured. They are all having negatively charged. If all the protein are negatively charged, they will move together according to the size, okay, to the positively charged electron. Okay, we cannot run 2D by having the second D with the negative, with the native gel. Okay. So what is the third D just now in the 2D electrophoresis? You need to analyze all these spots using the densitometer. The scanner. The scanner will capture or will grab the whole spot and then scan in the scanner. By using that software, it will just see the dot in 3D. Okay, this dot will become like a mountain or something. They will see either this dot is basically one dot, or it is two dots combined together and become bigger, or what. So that's where the third D comes in. Okay. So I think we need to stop for this section. We will discuss again for protein separation for the second part of the protein purification. So any question? Four slide. First four slide on this lecture. Okay. First four slide. First four slide. Let me check here. Where is first four slide? Hmm. Okay. So before you start to do the purification, we need to know what we're going to purify. That's why we need to know these properties of the protein. What kind of protein that we're going to purify. For our case, we want to purify T1 lipase. First, we check what is the size of the molecular, what is the size of the T1 lipase, the molecular weight of the T1 lipase. And then we need to know the charge, the PI of the T1 lipase. What is the PI of T1 lipase before we decide either we want to use what kind of method, like because we need to know or prepare the protein become positively charged or negatively charged. And then solubility in what kind of buffer? Same, is this like a buffer? Are we going to use that pH, or are we going to, is this protein okay in that kind of salt, or it just, will it become soluble in that salt or not? Okay, and then the fourth one will be affinity. We know that T1 lipase is having affinity towards nickel because it has histidine tag. So, okay, let's just go with that affinity chromatography using his tag. But if it is used GST, glutathione, then go for GST. So we need to know all these things first before we decide, before we start to do purification. For our case, we have started using affinity. Let's go with affinity. Let's check with that affinity. It works or not. Some of you having 20%, 30%, 80% recovery. So you decide. If affinity only gives you like 20% recovery or yield, forget about affinity. Use other technique. Okay, maybe IEX first for you. Okay. So second part, second section, we discuss about the protein separation using molecular weight. We have atlas navigation. It involves high-speed centrifuge, and then dialysis. Where we do the dialysis, we put the protein inside the tube. It looks like ice cream Malaysia tube. Yeah, it is whisking tube or something you call it. And then after that, we have gel filtration. Yeah, we have discussed about gel filtration, and then SDS page, and also native page. Gel filtration, it is about the size cutoff. We check what kind of, we have 43 kilodelta, then find the best metric for 43 kilodelta separation. Yeah, this is how it looks like. If we have gel filtration, 10 milligram of protein was loaded into 20 cm times 20 cm. The metric. And then this is the type of the metric, Cephadex G50. And then this is the equilibration buffer, 360 pH 7.5. And then the column was eluted with buffer around 1 ml per minute. The flow rate, and then collect with the each fraction having 2.5 ml per fraction. And then the absorbance of each fraction was measured with 280 nanometer, and then The 410, this is for the activity for the protein that they have purified. Okay. So here it looks like only this one is zero. But remember, we have also this peak, small peak. That's why they're checking the activity from here to the end or the last fraction. Maybe the one they are expecting is this tube. You see, 1, 2 fraction, 1, 2, 3 fraction. So this fraction number 40, 41, 42, this 3 fraction, basically, oh sorry, this 3 fraction, this 3 fraction 40, 41, 42, they are all your protein because it gives you activity when you check at absorbent 410. Okay. So yeah, this is about the first 4 slide. Um, okay, in the experiment we have done is 2D. No, basically in the last experiment we do is only 1D. We have done only this side, which is the second D, not the 2D. If you say 2D, meaning that you have run this IPG step, but you have not done this. That means you have only 1D. Okay, you have done last time with 7 cm gel. Okay, this IPG strip comes in different size, 7 cm, 12 cm, and 24 cm. If you use 12 and 24 cm IPG strip size, that means the gel will be bigger. It will fit the IPG strip. Okay, and then this IPG strip is not meant only for pH 3 to pH 10 only. This is broad range. You can also make it narrow range. Maybe if these two peaks is still close to each other, you want to make it narrow range. Maybe you want to use the pH 7, pH 5 to pH 7. If you have pH 5 to 7, okay, this part become 5, this part becomes 7. So the 6 we have in the middle. So it will just separate every point of it. Okay, you can always adjust, by this IPG strip in different range. Okay, for a start, for the beginning, you can use 3 to 10. But since you know already your PI is around 6.31. You don't want to use this 3 to 10. Maybe you want to use from 5 to 10 or 5 to 8 or something. Okay. So what else? Any more question? Okay. Since one of you asked about the volume, where is it? Yeah. So in size exclusion chromatography, right? So void volume is the volume of the buffer that we have used to fill up the space in between of the matrix. Okay, so total, this is where the void volume will take place. So when you inject your sample, when you apply your sample in your gel, in your matrix, in the gel filtration, for example G25, the G50 just now. So what happened if the void volume is 50 because we have used very long column. If we have used very long column, so the first, and then the column volume, I mean the size of the, I mean the column is 50. Oh, what happened? To blur. Check. Okay. So meaning that here to the first molecule come out, this is called void volume. Okay. Meaning that this volume is just the volume of the buffer before you apply your sample. Yeah, it is represented the volume of this, the buffer. You see, this is the metric, the metric of your where this metric we can track your protein, right? When you start applying your sample, this solution, this volume, this liquid will come up first. So volume of the buffer come up first. Basically, they are just a void volume. It's just a buffer in the column. It is not your sample yet. So if it is 100 mil, you don't want to start assaying your protein, your activity of your target protein start from 1 mil, 2 mil, 3 mil, because you know the first 100 is just the solution or the buffer inside this, right? Okay. So, any more question? We can have one more lecture about purification to complete all this part, because this is just introduction. Not really introduction, it's quite deep, but still, are you okay, guys? We're going to repeat this section since we cannot record this one, right? Okay, more question? I have another meeting later on. Priya, Nuraini, Divian, Farisha, all of you, Arbana, Adib, Zuhaili, Anis, Badrina, Arifah, Basil, okay, all of you, 70 of you. Any more questions? Okay, because could you please ask someone who missed, I mean anyone who missed this lecture, can just ask them to contact me personally so that we can have a separate Google Meet with them. Yeah, I'm so sorry, you cannot. Yeah, this is because of my internet connection. It's too bad. Okay, so I'm going to prepare myself for the next meeting. Thank you, guys. Hopefully, you can just have a look. We can discuss again, and then you can always set up a request for another meeting, for another lecture for the same topic. Okay, so you're welcome. See you guys, and then have a nice lunch.